Multiple linear regression. Craft beer. What purchases, or actually who purchases craft beer? The popularity of craft beer has exploded over the past 10 years, and analysts are interested in the demographics of the craft beer consumer. A market research company, Nielsen, purchased data from a major grocery store's loyalty program. Loyalty programs collect demographic data of their members and track their purchases. The following data set, which is on the next tab, consists of 30 consumers who purchased craft beer in the past year. Conduct the appropriate hypothesis to determine if the following variables can be used to predict the amount spent on craft beer in the past year: gender, male or female, age, the number of people in the household, and household income. Use an alpha of 0.05. You will need to use binary encoding for the variable gender. Code female as 1 and male as 0. Then you'll complete the coefficient table in this tab for the final model. If a variable was not included in the final model because the p-value is too big, put an A for the coefficient and p-value. So, we have these possibilities: age, household income, household size, and gender. And we're trying to see which ones are significant. So we start over here on the next tab, and this is where we're going to do most of our work. So, what we're trying to predict, the Y variable, is the amount spent on craft beer per year. These are possible X variables: age, household income, household size, and gender, in order to predict the amount spent per year. And we're simply trying to see which of these is statistically significant. But before we begin, we need to insert a column here in order to code gender. So we're going to give it exactly the same title, but this time with binary encoding. So we'll say if the value in this cell is equal to female, in quotes, then the person is a 1, otherwise the person's a 0 for male. And then we'll copy that down. Now the reason we had to insert the column this side is because all of the data needs to be continuous. In other words, next to each other, or contiguous might be a better word. Okay, now we can go ahead and start the data analysis toolpack in Excel and choose regression. So we'll go to the data tab, choose data analysis, pick regression, and here we have to begin with what's the Y range, in other words, what's being predicted. And what's being predicted is amount spent per year. And so you want to highlight that column, including the column heading, because the column heading is a label, and we're going to tell the regression that we have labels, see how that's checked. Then we'll pick the X range, and that is going to be all the X variables, including the binary encoded gender, but not including the old gender that was not binary encoded. Why? Because regression can only work with quantitative variables. So it's simply, well, actually it will refuse to work if you include this variable over here. So we do pick labels because we have the column headings, and we have to tell it what our alpha is. So we pick confidence level of 95%, which is equivalent to alpha of 0.05. All right, now for our output range, we want the output to appear right here. And it doesn't matter if you get this exact. We're just trying to place it over here to the right somewhere. All right, and here's our output. Now, while the output is still highlighted, and before you do anything else, really important, go back to the Home tab and change the formatting to a number. Make it a number with 2 decimal places if yours did not come up with 2 decimal places already. Use these increase, decrease decimals in order to get 2 decimal places. Why? Well, because remember, we're trying to match 0.05 or less, and that's pretty easy to see at 2 decimal places. So here we are. What we look for is the p-value. Here's our coefficients: age, household income, household size, and gender. And we look right over here to p-value, and we're looking for a p-value that's more than 0.05, meaning that it's not a significant predictor. And of those, we look for the one that is the least significant, in other words, the highest p-value. And that clearly is household size at 0.84. So basically we're saying it doesn't matter what your household size is, it's not going to predict your beer buying behavior. So we're going to take out household size and run it again. And the way we do that is we come over here and we delete that column. And then we go right back to our data analysis toolpack. And now the issue that we have, the Y range is still going to be perfect because we carefully set up the Y variable in the left-hand column, so it's going to know that. Right? Watch, I'll click on it just to prove it. See how the Y range is just where it should be. But the X range now is going to have to be reduced by 1, because if I choose X range, notice that it went out and grabbed that other column, because remember, I deleted a column, but it was basically picking up the same range as before. So now it's picked up this column. So I've got to redo the X range not to include the non-encoded column. Still labels and confidence interval. And now I want to place this one. I'm going to keep this one. I don't want to lose it. So I'm going to place this one just underneath it. I think it was there. Okay. It says regression, having trouble to offset input-output reference. All right, let's try to figure out what that means. Oh, as you can see, my X range didn't pick up what I wanted it to pick up. So I'm going to click back on that. Hopefully yours worked better than mine. Pick the X range again, come back in. Now it's correct. And I-26 looks fine as the output. Click OK. Okay, input range contains non-numeric data. I must have picked up gender by mistake. Let's try that again. Sure did. All right. Well, so I'm making all the mistakes, so hopefully you won't. So now pick it up without gender, non-binary encoded. And let's give it a try one more time. There we go. Remember, while it's still highlighted, so don't click off it yet, right back to the Home tab and choose number. So you want the 2 decimal places. Now you can see here that all the p-values, still not going to click off of it, all the p-values are less than 0.05. So this now is our final run. So I'm going to copy this while it's still highlighted. Now if you've clicked off of it, then please highlight it to copy it. And I'm going to come right back over here and place the final model right there. All right. Now, this looks pretty good, but I actually want to bring the data over here so that I can use it for predictions. So I'm actually going to reference all the values now here. So I'm going to put equals for the coefficient, and first the intercept, so that's the coefficient for the intercept. And then I'm going to do an equals and grab the p-value for the intercept. So the coefficient's in the first column here, the p-value is over here in the fourth column. And I'll do the same thing with age, equals coefficient equals p-value, right? These are all significant predictors because the p-values are all less than 0.05. Household income equals coefficient equals p-value. Household size equals, oh, well, we got a problem here. Remember, household size was the one that we got rid of. So we don't have a coefficient. So in this case, we put n/a. And we do it here too. All right, and gender equals coefficient equals p-value. And then finally, we're going to pick up the standard error. The standard error is up here. So this is the standard error for the whole big thing. There are other standard errors, which as you can see, there's a column of standard errors here, but we're not going to use those because those apply to individual coefficients. This is the standard error for the entire model. All right, so now using these coefficients, which we've calculated, we can actually predict with brand new data that's not part of the data set. So here's some brand new data that we're going to predict from. And here's how we do it. We're going to say the predicted amount spent per year is equal to the intercept. This is the regression equation, so it always starts out with the intercept. Just like back in middle school, you did y equals mx plus b, so b is the intercept, so we're just putting the intercept first in this case. And we're going to lock that because I'm going to copy this formula down. So Command T on a Mac, or F4, or function F4 on a Windows machine. Plus, and then we take the coefficient of age, which again we lock because we're going to copy this formula down, times the value of age in this test data that we're trying to predict from, which is not locked because as we copy the formula down, we want it to pick up the next rows here. Plus household income, which we lock, times household income here, plus, all right, we're skipping household size because that's an NA. So we'll jump over here to gender, which we lock, times the gender value here. So this is our equation. Notice that we've simply left household size out. It still appears down here because it's part of the data, but it's not being used as a predictor. All right, so what we're predicting is for someone aged 25, the household income of $51,000. Again, household size, not a predictor. And gender being male, that we expect that person to spend $397.70 a year on craft beer. And we can even copy that formula down. So we get a prediction for this next row. And we even get a prediction for this last row, but this one's obviously way off because we haven't filled in the data yet. You will when you, as to answer one of the multiple choice questions. All right, now we can also create a prediction interval using this standard error because we now know that all our predictions are going to be off on average by $46, right? And to get a confidence interval of 95%, we kind of want to go, it's almost like the empirical rule in reverse, right? To pick up 95% of the values, you've got to kind of go out 2 standard errors either side, and that's exactly what we're going to do. So we say equals this value plus 2 times the standard error, and we're going to lock that because it's in another table. We're going to copy this, then drag that down. And then on the lower end, we're going to say it equals that value minus 2 times the standard error, and lock it too. And copy that down. So in other words, we're saying, look, we're going to predict, given this data, that the person will spend $397.70. We could be wrong, but we're 95% confident that given this data, the person will spend somewhere between $303.85 and $491.55. Okay, now we can go for the multiple choice questions. So the first one, and you'll need to sort of keep this data in view as you're answering these questions. Use the experiment row in the prediction table to predict the annual amount spent for a 30-year-old male, so age is going to be 30, household size 5, which you're going to put in there, even though we now know that that's not even going to be in the regression equation, but we'll still include it. Household income of $62,000. And this is a male. So female is 1, male is 0. And we get a prediction of 375.46. Come over here and we see that that is option C. What's the interpretation of the standard error of the estimate? This number right here. And it is choice C. On average, predictions differ from actual spending by about, right? So each of these predictions on average differs from actual spending by about $46.93. What's the interpretation of the adjusted R squared? So let's go find that number. It's up here. It's rounded off at 69% or 0.69. All right. And so let's look at our choices. All right, so adjusted R squared is about variability, how much variability is explained by the model. So about 69.2% of the variability in spending is explained by variability in age, income, and gender, right? Not household size, because we said that's not a good predictor. So we'll pick B. Now we get to really interesting questions about interpretation of the slope. And this one's kind of tough, but because of the binary encoding. But if you kind of get it right the first time, the binary encodings will become pretty easy eventually. So 0 male, 1 equals female. So let's look at the coefficient. And you'll see that the coefficient is negative. So in other words, if the person is a female, they're going to spend $96 less than if the person is a male. Why? Because if it were a male, it would be 0 times this 96 negative, in which case it would go away. But if the person's a female, then it's 1 times this 96 negative, which means it stays in the equation, doesn't drop out, doesn't zero out. And so you're going to spend less money if you're a female. So let's see. And it looks like D, 96.46 less for females, holding age and income constant. Okay. What's the interpretation of the y-intercept? Well, the y-intercept would only come into play to be interpreted if we had put straight zeros for all of the test data. And it's kind of what we had. I don't know if you recall back down here, but before we put in the test data, the value here actually was the y-intercept because all the other terms in the equation turned to 0. If you don't remember that, then when we do the next problem, take a look. When we drag this equation down, and you'll see whatever value is here is actually the y-intercept until this data is filled in. So what's the interpretation of the y-intercept? So spending, let's look at the choices. Spending is 506 for someone age 0, income 0, and male, in other words, where everything is 0. And that indeed is the correct interpretation because it's a positive number. Now, obviously that's kind of meaningless in a way, and we rarely do actually interpret the y-intercept, but nonetheless, good to know. All right, what's the correct regression equation? So that's this equation that we did right here. And here, to get this, to choose the right answer, you just got to make sure that you get all your signs right. So the intercept was positive, age was negative, income was negative, household size wasn't even in it, and female was negative. So really, all the coefficients were negative. That's like a huge hint in which one of these is correct. So we need the y-intercept to be positive and all three of these to be negative. A would kind of work on that. B would not. Let's look at C and D. D would not because you have positive coefficients. So it's probably going to be A or C. So let's see if there's something tricky between them. And as you can see, there is. In A, we break the pattern of plus times, oops, that's times. It's supposed to be plus times, so it must be C. What's the interpretation of the slope for income? So it's 0.71 negative. In other words, as your household income goes up, you actually spend less money. Kind of weird, right? If you think about it. But as household income goes up, you spend less money on the craft beer. So, spending, and how much less? Well, 0.71 dollars less on the craft beer for every $1,000 of income. So spending is 0.71 less. Or spending falls, I guess. It's not is, but spending falls 0.71 for each extra 1K of income, holding age and gender constant. There's our answer. And what's the interpretation of the slope for age? All right, so let's look at age. That's also negative. So as your age goes up, your spending goes down. So for every year older you get, you spend $288 less. So it would have to be spending falls, $288 per year of age, holding income and gender constant. So that's B. And we're all done with this one.